don't want your telescope doing this. You want it doing something like this, very cold. And for the kind of objects we're looking at, it has to be extremely cold. Now, the next thing is, why do we want to be in space? Why not just build a big telescope on the ground? Well, the problem is that on the ground, this is what we call atmospheric opacity, and this just shows the wavelengths where the atmosphere absorbs radiation. And you can see here that it's really not that great in the infrared. And the other problem is, not only does the atmosphere absorb infrared radiation, it's not very stable. It varies from night to night, even from hour to hour if you're sitting on a ground-based telescope. So if you want to do infrared astronomy, the best place to be is above the ground. Okay, now the next thing I want to talk about, and this is, now we're starting to get to the really big differences. Why is JWST so different from Hubble? So Hubble sits in what we call a low Earth orbit, and this picture just captures that perfectly. This is the Earth, this is Hubble, and Hubble goes around the Earth every 90 minutes. And 45 of those minutes it's on the day side, and you have a nice bright Earth, as you can see here, which creates a lot of scattered light. And then for 45 minutes it's on the dark side, and you've got the dark Earth. And for those 45 minutes you can do science, you can do astronomy, without having a nasty background contribution from the Earth. The problem is worse than that, though, because every 45 minutes you're going from day to night or night to day, and that's a very significant, what we call thermal perturbation or upset. You're basically going from day to night. And for this telescope, it means that Hubble gets very cold and very hot, every 45 minutes. And we still do great science with Hubble because it's been designed to cope with that. But we do actually see the effects of this when we look at Hubble images. Hubble actually does what opticians call breathing. The focus changes by about 3 microns every orbit as it expands and contracts from going from cold to hot to cold to hot. And you can't see that very easily in Hubble images, but if you have a bigger telescope, it starts to become extremely noticeable. So putting telescopes in low Earth orbit, we've kind of reached the limit of what we can do there. And especially if we want to do infrared, we want to get away from the Earth. Another reason is that this bright Earth is also very bright in the infrared, so you really don't want that background in the infrared creeping into your telescope from the bright Earth either. So for JWST, one of the really big differences, we're putting it in an orbit that's very distant from the Earth. And this shows you what I mean. So the Earth is here, and this is the Moon. And if you imagine this is a line coming from the Sun that passes through the Earth and continues out, JWST is going to be at a place called the second Lagrange point, which is a point that's supposed to be quasi-stable. One of these wonderful mathematical things. And it's about 1.5 million kilometers from Earth. And the reason we put it out there is because it has a very benign thermal environment. It's not heating up and cooling down all the time. And it's also able to observe every minute of the day. And the only time we stop observing is when we go to the next object. We aren't being continually interrupted with these 45-minute zooms around the bright Earth. It's far enough away. It's completely benign in the sense that it has no major thermal perturbations. And this here is just another illustration. So there's the Sun, the Earth, and the L2 point's about here. And we don't actually put it at the L2 point. It actually orbits the L2 point. And what that means is we actually have to do what's called housekeeping every few weeks. We have to do a small burn just to move the telescope back and keep it on that orbit going round L2. And as I said, this is 1.5 million kilometers out to here. And then this is about 700 or 800 million kilometers around the L2 point. So that's one of the big differences. And then the final difference is, how do we launch this telescope? Now, you probably haven't seen yet just how the scale of this telescope compares to other telescopes, but this picture here shows the Goddard Space Flight Center team, and this is only a part of the the JWST team, but it's a very large telescope, and as you can see, even in the largest variant possible, it really doesn't fit. So we have to do something else that we've really never done before, which is fold the whole thing up and then unpack it once we get into space. And for people that do space science and space missions, that's kind of anathema. But generally, we like to have as few moving parts as possible, because then in space, if they break, well, they can't break, and we try to make them redundant, so if they do break, we have a backup. So we're really going into new territory here with the notion that you fold this telescope up and it's kind of like taking an origami puzzle apart and going back to the original piece of paper. So we really have a very different philosophy for this telescope. And as I said, you can see just how big it is. It's a very large piece of hardware. So the final thing I want to say is how do you, or why are we doing this? This telescope was done by a colleague of mine, Martin Harwitt. And what it shows is how, as we've gone from the discovery of the very first telescope through the ages with ever increasingly large telescopes and new techniques for doing observations, we've expanded our capability and made new discoveries. So every sort of expansion by something like a factor of 10 brings a new discovery and a new understanding of the universe that we're looking at. And you can see it's kind of accelerated since the 1900s. And the things that kind of helped us accelerate were this jump in mirror sizes on telescopes on the ground. The Hale telescope's a good example of that. And then the advent of photography, which really gave us a big boost in what we could do. We weren't just looking with the naked eye anymore. And also we could actually record what we saw photographically. And more recently, around the time I started working in astronomy, we started getting electronic detectors, initially TV tubes, and then we went to electronic sensors like CCDs. And most of you have got a digital camera, I would imagine, and a good number of those have CCDs in them. So this is a technology that I would say astronomy has kind of brought to the world, if you like. And then when we flew Hubble, that really gave us an absolutely amazing jump in capability because we'd never been able to look above the atmosphere before. And Hubble's just given us so many new discoveries and, as you heard, really changed the way we think about the universe. And we think that JWST is going to do the same thing. So this is part of our sort of track in astronomy, that you bring online new facilities to address science issues that you want to understand. And these new capabilities not only solve those problems, but they also allow you to make new discoveries. So what is JWST being built to do? Why are we doing this? Well, JWST has a number of science themes, and basically we're trying to track a number of subjects, but we start with the Big Bang, and what we're trying to do is discover the very first stars that formed in the universe after the Big Bang. Then we're trying to understand how these stars and the galaxies they're in formed and how they've evolved across time. We're trying to understand how stars and planets form. And then we're trying, if it's at all possible, to look for signs of life on those planets. And this is my daughter. I thought this was a nice picture to put up. So, one of a couple of the big goals in astronomy right now are to understand first light and to understand how, the early universe formed, and also to understand or to detect extrasolar planets and look and see if we can find not life, but evidence that there might be life. For instance, molecules that you see in our own planet's atmosphere. So I'm going to talk a bit about first light, and then I'm going to move on and talk in some more detail about planets and the detection of molecules in their atmospheres. So JWST's first light goal is this, and basically what we're trying to do is identify the first objects that formed in the universe, either star clusters or proto-galaxies. And this basically is a history of the universe from the Big Bang back here all the way to present day. And we think the first stars formed something around 400 million years ago. And right now with Hubble, we've been able to see back to about here, about 1 billion years after the Big Bang. So there's this whole area in here that we're building this telescope to explore. Now, there have also been a number of observations of the afterglow pattern of the Big Bang, first by COBE, with observations made by my boss, Dr. John Mather, who's the senior project scientist for JWST, and he won the Nobel Prize for these observations. And then more recently, another mission called WMAP has come up with an even more detailed design showing the perturbations in this afterglow that are the source of the formation of the early material in the universe. So, what is first light? It's basically defined, as I said, it's the first galaxies or superstar clusters. And the way we look for those is we look for a change in what's called the luminosity function. And basically we take very deep images and we just keep looking for more and more distant observations of galaxies. And at a certain point, the number of galaxies will start to change and roll off. When we found what we think are the most distant objects, we can look at their composition by taking spectra. And from the spectra, we can understand if these are the very first objects or whether they've already formed second or third generation stars. And so once we have our targets, we can look for what we call metallicity, and then we can also do mid-infrared observations and look for second or third generation stellar populations. Now, why are we doing this, and what has Hubble done already? Well, this is the Hubble Ultra Deep Field, which was taken with the Advanced Camera for Surveys, and this observation, which was something like 400 orbits of Hubble time, is the deepest ever image of the universe. And you're seeing a lot of very faint objects in this image. But the objects that we're trying to find at 400 million years after the Big Bang, their light is redshifted so far into the infrared that they're the objects that we can't actually see in this image because this image stops at around 1 micron. So we're basically looking for even more distant objects than this image here, and they're the reddest ones that you don't see because the camera only works in the visible. Most of the faintest objects that we found in this image go back to about 1 billion years after the Big Bang, or a redshift of around 7. And I got some nice images here which just give you some examples of just how powerful these cameras are now. So when I started doing astronomy, people were struggling to get ground-based images of objects that are around this redshift. And now with the Hubble Ultra Deep Field, we can see things that are 1 billion, 2 billion years after the Big Bang, and we can actually see structures in them. People think that this object here has this long red jet there. This is another very distant object, and then this is the most distant object that they've found, I believe, which has a redshift of 6.7. So it's not quite 1 billion years after the Big Bang, but it's close. And this object here just shows you what we've been able to do with the limited ability to look at these objects that we have right now. So we can't see much further back than about 1 billion years. But we have been able to take the Hubble Space Telescope data and Spitzer data for some objects and start to show how we would do this. So this is a visible image, and you see that this red galaxy doesn't appear in the visible image, and that's because its light is so far redshifted into the infrared. This is an infrared image taken with Hubble. It's a very short wavelength one. It's about 1.1 microns, and you see it starts to appear at 1.1 microns. And then this is the Spitzer image, and you can see that it's nowhere near as sharp as the Hubble images, and we do detect that object. So what we need to do next is build the bigger mirror with the cold optics so that we can start to push even further back than this to find these very first objects. Another thing that we can do right now, and there's a number of observations that do this already, is if you like, cheat a bit and use some of the tools that nature provides to look for very faint, very distant galaxies. So this is what we astronomers call a gravitational lens, and you see there's a lot. It's a supercluster of galaxies. There's a lot of yellow galaxies here, which are what I'll call the foreground galaxies. They're very distant. And as Einstein predicted, that cluster of galaxies, there's so much mass in it that it acts as a kind of lens, and it bends lights coming from objects even further back in the universe. And this is what you're seeing here. You can see there's a big red streak here. There's another one here. There's a number there. So these streaks are actually objects even more distant than this cluster being re-imaged, or their lights being bent around this massive cluster of galaxies. And it turns out that you get a kind of magnification effect, so you can actually look for objects this way. Now this just explains how that works. So this is your background object. These blobs here correspond to those yellow clusters.